In this video, we are going to look at neutralization reactions. Recall that a neutralization reaction is just a reaction between an acid and a base. It is just a reaction between an acid and a base. Also recall that the products are always water and a salt. Remember that in chemistry, a salt is any ionic compound. So a salt is any ionic compound. The neutralization reactions also follow double displacement reactions. So you'll still have the AB plus CD is going to yield AD plus CB. In this reaction, when you have an acid plus base, you're going to yield water plus a salt. And that salt is going to be what is left over after taking water out of the equation. So if I have HCl and sodium hydroxide, this reaction blows my mind all the time because we have hydrochloric acid, one of the strongest acids we have, sodium hydroxide, one of the strongest bases we have. Literally, if I drank either of these, I would probably die. They are not good for my body. If I get them on my hands, they can cause burns. It is a very dangerous situation. But if I mix them together, you can see we have the hydrogen part of the hydrochloric acid and the hydroxide part of the sodium hydroxide. And those are also my A and D, and they will produce water. So when this reaction starts, we're going to get H2O. Realize that HOH is the same thing as H2O plus the leftover salt. So after I take hydrogen away, I'm left with chloride. After I take hydroxide away, I'm left with sodium. So the cation that is left over is sodium, and the anion that is left over is chloride. Now, sodium is +1, chloride is -1, so this is charge neutral as I have it written. Water I know has a state, it is liquid. Water cannot be aqueous because if we mix water with water, we just get more water. It doesn't become aqueous. Now, the other component of of the products, is sodium chloride. Sodium chloride has sodium. It is part of the N rule, so I know that this is going to be aqueous. I just want you to realize that we literally just made table salt water. We literally just made salt water. So when you take the strongest acid or one of the strongest acids we have and react it with one of the strongest bases that we have, you can make something that you could drink. Isn't that insane? I just think that is crazy. So let's get some practice at predicting the products for neutralization reactions. So right away, for all three of these, it's a neutralization reaction, and I know it's a neutralization reaction because I have something that starts with H and I have something that has hydroxide in it. So for all three of these, I know they're neutralization reactions, so I can write water as my first product for all three of these. Look at that. I just got 50% of my products on all of these. Now I just need to round up, if you will, the leftover anions and cations. So after I take water out of sulfuric acid and potassium hydroxide, the cation I'm left with is potassium. And the way you can think about it is you literally can just cross these out too. And you can see I'm left with potassium and sulfate. Now, something that you need to pay attention to is sulfate requires two hydrogens in order to be charge neutral. So that means the charge on sulfate is going to be 2 minus. Potassium is also a plus 1. So that means we're going to need two of them as well. Now, to balance all of this, I would put a 2 in front of my potassium hydroxide, and then I would put a 2 in front of my water. When I'm balancing neutralization reactions, I always like to start with the salt. So the first thing you want to do is start with the salt. So balance out the salt. So I did that with my first example, with the first problem here. I put a 2 in front of my potassium hydroxide. The next thing you're going to do is the total number of hydrogens in your acid will be the coefficient for water. So let's go through this together. Potassium is not balanced. I start with my salt. I put a 2 in front of my potassium hydroxide. I have one sulfate here, one sulfate here, so I don't need to balance it. It's already balanced. In my sulfuric acid, I have two hydrogens. So that's why we put a 2 in front of our water. The final thing you want to do is double check that it worked. And so you can go through and see if you have the same amount on each side. And for this one, we do. Now, potassium is in group 1. I know that all metals in group 1, all ions of metals in group 1 are soluble, so this is going to be aqueous. All right, let's round up the cations and anions for our next problems. So if I go through and I take away my hydroxide and hydrogen, I can see what is left over. I have calcium and PO4. I notice that I need 3 hydrogen to make a charge neutral compound with phosphate. So phosphate's going to have a 3 minus charge. Calcium is in group 2, so it is going to have a 2 plus charge. So in order to make this charge neutral, I'm going to need 3 calcium and 2 phosphates. So I'll put a 3 after phosphate after calcium. And then remember, in order to show that I have 2 of my phosphates, I'm going to put a 2 outside of parentheses around the phosphate. So let's go through our balancing. I'm going to start with my salt. I'm going to erase my X's so we can see everything nice and clear. Start with my salt. I have 3 calcium in my salt, so I'm going to put a 3 in front of my calcium hydroxide. I have 2 phosphates, so I'm going to put a 2 in front of my phosphoric acid, and that will make it so I have 2 phosphates. Now, since I have 2 of these and there are 3 hydrogen in each one of these, I'm going to have a total of 6 hydrogens. And the total number of hydrogens in your acid will be the coefficient. So that means I'm going to write a 6 in front of my water. And then we can double check. We have 12 hydrogen here, 6 hydrogen from my calcium hydroxide, 6 hydrogen from my phosphoric acid for a total of 12. I have 6 oxygens from my water. I have a total of 6 oxygens from my calcium hydroxide. Remember, if your polyatomic ions don't change, don't break them up. So that's why I didn't count the oxygen from the polyatomic ion. I have 2 phosphate in my reactants, 2 in my products. Now, the last thing I need to do is find out the state of calcium phosphate. So calcium phosphate is not something we can use the end rule for. So let's go back to our solubility rules. When we look at our solubility rules, I see phosphate right here. So most compounds with phosphate are going to be insoluble, except for ammonium and alkali metals. Well, calcium is not one of those, so it is going to be a precipitate. It's not going to be soluble. So the state is going to be solid. So this is a little bit of a special reaction because it is both a neutralization reaction and a precipitation reaction. It's kind of cool, and they both fall into one reaction. All right, let's look at our last example. Water is my first product. The cation that I have left over when I take HOH out is strontium, and then I have fluoride. Strontium is in group 2, it has a +2 charge. Fluoride is in group 7, it has a -1 charge. So, in order to make this charge neutral, we're going to need SrCl2. If we look at our solubility rules, we'll see that most halides are soluble. There are 3 exceptions where they're not. Strontium is not one of them. So my state is going to be aqueous. I'm going to balance this by starting with my salt, put a 2 in front of HCl, and the number of hydrogens in my acid now are 2. And I have 2 already in my, or so I need to put a coefficient of 2 in front of my water. My pen is really not doing well. If you know what's wrong with it, send me an email and let me know. And if that's what's wrong with it, I'll give you extra credit. All right, go ahead and double check. Make sure that we have the right amount of hydrogens and oxygens. And as I'm looking at this, there's a typo. Strontium is in group 2. So this should be a 2 right here, not a 3. I apologize for that. When we are looking at neutralization reactions, we have a technique called titration. And titration is used in a laboratory setting where you can analyze the concentration of a sample. We use what is called an indicator that will change color when the reaction is complete. So in this example down here, we have an acid reacting with the base. The base is up here in our burette. This is the glassware we use for a titration. Our acid is down here in the Erlenmeyer flask. We also put the indicator down here in the Erlenmeyer flask. Our acids and bases are generally clear and colorless, meaning that you can't really tell what is in each of them. And if you don't know the concentration of something, you can use this technique to determine the concentration. So I start to add my base, I add it even more, and you can see that we change color. So this right here is called our endpoint, and that is where the moles of acid are equivalent to the moles of the base, and you can use stoichiometry to figure out how many moles of acid you have in your solution. If you keep adding indicator, you'll notice that the color will become darker and darker, and that is when you have gone past your endpoint. And so now there is just a lot of base in there.